Hello, my name is Alexander Schatten. I'm talking today with Dietmar Winkler, who is Senior Researcher at the Christian Doppler Lab. Maybe you can introduce yourself briefly.
Yes, I'm working at the Christian Doppler, as I said before, with focus on process management, quality assurance, empirical software engineering, and I think it's the point why I'm here and talk about some quality assurance in context of the research project.
Because we had some videos recently about general challenges and technical integration, and let's go into the topic. Why is quality assurance an issue in the domain?
Yeah, the main problem in automation systems engineering is that we have to deal with different stakeholders, with different tools, with different disciplines who have to interact with each other regarding, for example, electrical planning, for example, pipe and instrumentation software, and so on.
And so on this figure, for example, we see this visualized by these circles, and for example, the blue circle would represent electrical engineer, or
the blue circle is connected to the process engineer in this figure.
Okay.
And every discipline, for example, the process engineer have his own tools,
okay,
who model and design the physical layout of the system.
Okay.
You have the orange part is the electrical engineer,
okay,
with circuit plans and so on, dealing with electrical signals. We have software engineers is the green discipline, who works, for example, with UML and so on.
Okay.
And in the middle part, you see the circles, which are
the white areas.
The white areas are the common parts. They are the overlapping parts between different disciplines. From our industry partners, we observe that signals is a common concept who connect different disciplines to each other, which are represented by the white parts in the middle of the figure.
So, can you? I'm not quite sure if I understood this. What does the concept signal originate from?
The concept signal comes from the electrical engineering and is some kind of information which is exchanged by different disciplines. For example, the electrical engineer is dealing with some wiring and so on. The software engineer...
wiring some components of a plant, for example, or of a machine or something like that.
Right.
Okay.
On the other hand, the software engineer deals with software variables, and typically they are not connected to each other, but they can be compared to signals which are connecting these two components from the electrical part, for example, to the software part.
So these are the common concepts that we can see in
that's right,
in the center. Okay.
And one interesting part is that we can address, if we identify the common concepts in the central part, in the white areas, we are able to identify different types of defects, for example, wrong defects, if they're not connected to each other correctly, or some missing components, and so on.
Okay. What would be the solution approach, or what is the solution approach that we are following in the lab?
The solution approach is in general the engineering service bus with some kind of technical integration. Technical integration means that we have to connect the tools to the engineering service bus.
That's the first step.
That's the first step. The second step is that we have to bring together the meaning of the signals of the individual data models. That's a semantic part of the solution approach. And on this figure you can see a simple example from the electrical and the software discipline. The electrical discipline dealing with electrical plan with its own data models.
On the left side, okay.
It's on the left side, right?
Yeah.
You have different individual data models for electrical planning, and we can have the individual signals in the signal list. For example, it's on the left part in the table, and similar is on the right part with the software models.
Yeah.
We have software variables, for example, and our approach for semantic integration is to link both disciplines to each other with a signal as common concepts.
So I understand it correctly that both are talking about the same things, but they might use different tools and a different language.
That's right.
And different semantical concepts to address the same things, and the goal is to integrate these
to each other. And the one big advantage is that every discipline can work in its own scope, and only the common parts.
So they don't have to learn new concepts or new...
That's right.
Okay.
And only the connection is done by the signal as common concept, and they can exchange data models and so on, and can interact.
Can we maybe illustrate this on a concrete example so that it gets a little bit more vivid?
Sure. As I introduced before, we have the end-to-end test.
Yeah.
It's some kind of high-end test for automation systems. That means we see on the figure on the left-hand side the sensor. It's a wired sensor in a machine or whatever.
The sensor could be, for example, a temperature sensor, pressure sensor, anything.
Or something like this,
okay.
Yeah. On the other hand side, on the right side, we have a software variable for application, for controlling, and so on. And the connection.
So software variable means it's a part of the computational system of the
control application.
The control application, okay.
For instance, and in between we have a system interface who connects them physically. For example, the wiring is connected to the system's interface and transferred to the software variable at the end. There are three different disciplines in this way.
And we also see that these three parts are engineered by different engineering disciplines with different tools and so on, as we mentioned before.
That's right, yes. And that's the main point for technical integration, or the main foundation for technical integration and for semantic integration. And we can identify defects quite easily in this way, as illustrated in the figure. For example, we can identify if a sensor is not connected,
okay.
For example, sensor S3. Or on the other hand, the S5 is, for example, connected to the system's interface, but not to the software variable.
Okay.
And in real world, it is difficult to identify these defects because everything is paper-based, or you are at the machine and have to measure data. And using this approach during development, you can identify defects quite early. And you can identify if the sensor is not connected anyway to a software variable, and that's the main idea of the end-to-end test.
So the conclusion is you target by a layering of technical integration, semantic integration, and other quality assurance methods to provide end-to-end tests that include the machines, the signals, until the controlling application.
That's right, yes.
Okay. Thank you very much for the talk.
You're welcome.